Today we are going to be finishing our last week of mole conversions, introducing one last conversion factor called the mole ratio. And the mole ratio involves a balanced chemical equation. So we will see how building that skill in a previous unit will help us to convert between compounds that are related in a reaction using their coefficients. So this process of changing from one compound to another is called stoichiometry. Sounds like a big intimidating word, but it's just another type of mole conversion using a balanced equation to convert from a reactant to a product. Maybe you know how much reactant you are using and you want to know how much will be produced, or vice versa. You want to know how much of a reactant to use in order to make a certain amount of product. So our stoichiometry, like I just said, any stoic problem is the process of performing mole conversions in which the compound changes. Up until this point, we haven't been changing the compound, we've been changing the unit, let's say like grams to moles, or molecules, or liters, using our three other conversion factors from this unit: molar mass, molar volume, and Avogadro's number. But we've always been using the same compound. Now with stoichiometry, we can change the compound as long as they're related in a balanced chemical equation. So those compounds must be related by an equation. And that's where the mole ratio comes in. A mole ratio is a ratio by which those compounds are related. So when I say related, we're talking about how they react or are produced in a reaction. And the factor of their relationship is the same as their coefficients in the balanced equation. So our ratio is represented by those coefficients. In a balanced equation. We can use a mole ratio as our fourth and final conversion factor for this unit. Just like I said before, molar mass, molar volume, and Avogadro's number are our other three. And mole ratio is our fourth and final mole conversion factor. Let's take a look at this more example to get an idea of using a mole ratio from a balanced chemical equation. So I have, in this example one, we've got kind of a picture reaction of making a s'more. And then underneath you'll see, here's our balanced chemical equation. 3 chocolate pieces, 1 marshmallow, and 2 graham crackers makes 1 s'more. We could have a 1 right there for our coefficient. So how much of each ingredient is needed to make 1 mole of a s'more? So whenever you see the word mole, remember that's quantity. So you could even replace that with 1 piece or 1, substance of our s'more. So whenever we're counting, this would be 1. So if I were to make 1 s'more, I'm going to need 3 chocolates based on this recipe, 1 marshmallow, and 2 graham crackers to make 1. And so we could actually put these all equal to each other and saying that if I have 3 chocolates, that means I can make 1 s'more as long as all the rest of the ingredients are available. If I have 1 marshmallow, then I can make 1 s'more as long as all of the other ingredients are available. And 2 graham crackers makes 1 s'more, as long as all the other ingredients are available. So this is referring to our mole ratio, that those coefficients in the front, and we can put them equal to each other. 3 chocolates equals 1 marshmallow equals 2 graham crackers and 1 s'more. And we can mix and match with those as our conversion factors because of that set ratio that will be true of our values for this particular reaction or recipe. You can use it in this next one by thinking about how many you are making and then taking the multiple of what your ratio is. So for example, we have 3 s'mores this time. If I'm going to make 3 s'mores, that means I'm going to need triple the amount of ingredients. And so if we're asking how many moles of chocolate or pieces of chocolate to make 3 moles of s'mores, if every single 1 s'more needs 3, then it will be triple, it will be 9. So I'm going to set this up in a conversion so that you can see how we would work with this. 3 moles, here's our given of the s'more. Do some train tracks here. And using our mole ratio, we have 1 mole of s'more is always going to equal 3 moles of chocolates. So there's our mole ratio step using the coefficients as a conversion factor. It's sort of like doing proportions, where we say if 3 is in 1, how many is in 3? So using that idea, this is just another way to set up a proportion. If you've used proportional fractions before in math class, that's kind of the idea, just set up using our train track conversion method. So this would be 9 moles of chocolates using that mole ratio. Now, sometimes we have lots of ingredients in our lab, or if we're talking about food, in our pantry that are available, and there's going to be one ingredient that eventually will run out first. And we call that the limiting factor, or our limiting reactant. So in this example next that we're going to read, we want to know which ingredient will limit us based on how much we're bringing to this bonfire. So you bring a candy bar containing 12 chocolate rectangles. So I'm writing down all the things that we have available. 12 chocolates, a bag of 30 marshmallows, and a box of 40 graham crackers. How many s'mores can you make? Well, that depends on which ingredient we're looking at. So we're going to actually take a look at each of our ingredients and say, okay, if I have everything else, how many can I make? So from my 12 chocolates, I can make a total of 3 s'mores. From my marshmallows, I can make 30. And from my chocolates, I can make 20, since I'll need 2 for each. So if I have used up all of my ingredients, I can really only make 3 with all ingredients present, because after that, once I get into the 4th s'more, I will have no chocolate left. I will still have graham crackers and marshmallows, but according to our equation, that is not the recipe for a s'more. So my ingredient that will limit me is going to be my chocolate, and my leftover or my excess ingredients is the marshmallow and my graham crackers. Now let's go back up to the top and define a few more terms. So the first term we're going to talk about is theoretical yield, and I'm actually going to leave it here for a second while I talk about it, and then we'll go define it. The 3 I just circled is our theoretical yield, which means, actually, you know what? This isn't 3, this is 4, because each s'more uses 3. 3 times 4 is 12. So in the fifth one we would run out. But our chocolate is still the limiting reactant. So 4 is our theoretical yield, which means that is the amount we will be able to make from our given amount of ingredients. In a reaction, that's going to be kind of based on our calculations, and that's why we call it theoretical. But maybe I burned a marshmallow, or I dropped some chocolate on the ground, or I broke some graham crackers, and I end up really only being able to make 3 complete s'mores. Then that would be my actual result, or my actual yield. So theoretical has to do with what we calculate, and actual has to do with what you can truly make or do truly make in real life with error taken into account. So defining that term, theoretical amount or theoretical yield, is the amount of product usually in grams, okay, that is produced in a reaction. And this is based on calculations. And just like we said, our calculations aren't always a perfect picture of what will happen in real life. We make error, and so we will have a percent yield, which is an error analysis, which will compare our theoretical to our actual. So an error analysis tool used to compare theoretical and actual yield. And we're going to calculate that just like you would for any other percent, part over whole. Like in our example, I said our actual would be the 4 if we burnt some or broke some, and the theoretical would be the theoretical would be the 4, and our actual would be the 3 if we burnt some or broke some. And so my actual is the part, and theoretical is my whole, times 100. So my percent yield for the example I just gave would be 3 over 4, 75% yield of my s'mores. If I could make all 4, then I'd have 100% yield. And our last term here is our limiting reactant. This is the ingredient or reactant that runs out first in a reaction. So this is going to be the factor that limits the amount of product that can be formed. And in our example, that was the chocolate, because we had the least amount of chocolate. And then the other ingredients are going to be your excess reactants. So our 3 terms: theoretical yield, percent yield, and a limiting reactant. Theoretical yield is the amount you can make based on calculations. Percent yield is your error analysis of actual divided by theoretical, and your limiting reactant is how much you run out of first. We're going to do a part 2 video for example 2, so join us for that to do an actual chemistry example.